dimension of this space?
8.
It's 8, right? It's 8-dimensional. It means that you can choose 8 of these numbers however you like. The last number on the diagonal has to cancel out the other 2. So it's an 8-dimensional vector space. So I'm going to ask you one more follow-up. I always like these follow-ups. And again, let's say that you got the basis wrong. I would then grade this next question on terms of what you had written down, right? So what I would like us to do now for part C, or whatever the follow-up is here, I would like to extend that to a basis for M3 of R. So extend the basis. This I know we've talked about, right? So follow-up, the last part of the follow-up, extend the basis for S above to a basis for M3 of R. Okay, so this will be a good example. Okay. Let's see what you guys think. So when I say extend the basis, I'm just going to call this extended basis beta. Obviously, I have to keep all of the basis vectors that I already have, right? So I'm going to keep, I'll write them here, E11 minus E33, E22 minus E33, and then E12, E13, E21, E23, E31, and E32. I'm going to keep those 8 basis vectors, and I'm extending this to a basis for M3 of R. What do I have to do in order to do that?
You have to take vectors in M3 of R that aren't already there, and add it to your basis.
Let's think. That's right. We need to think about adding some additional vectors that are not already spanned by the ones that are there. Okay. So can somebody give me an idea of what we might throw in here? We've got to make a little bit more room, obviously, but we're looking for a vector that's not here, that's part of M3. At this point, we can basically just throw in any vector that's not in S. That would just be any vector that does not have a trace of 0.
Are we looking for a 4x4 matrix or a 3x3?
No, everything is in M3 of R. 3 by 3. So we're looking for a 3 by 3 matrix. Well, actually, let me ask you another question. How many matrices am I looking for?
One more? One?
Why only one more?
Because there's like 9 spaces.
Yeah, M3 of R has a dimension of 9. Okay. It's great when you know the dimensions of your spaces in advance. So M3 of R is 9-dimensional, and I have 8 vectors here. Any basis for M3 of R has to have 9 vectors in it, and I've already been told that I'm supposed to keep those 8. So I just need one more vector, and it's supposed to be not in the span of the ones I already have. So there's many right answers here. This is not limited to one choice. Can somebody give me one correct answer? Go ahead, Jessica.
I'm going to guess that it's E33 because I feel like something has to do with that negative X plus Y.
Okay, here's the thing. What is the trace of this matrix? E33 is this matrix here.
Oh, it's only 1?
The trace is 1, right? So is this a good matrix to use?
Well, it's outside of what we already had.
Right. This is not in S, right? So this is a good one to choose, right? We just have to choose anything. There's lots of right answers. I just have to choose any matrix that does not have a trace of 0. So guys, let me just remind you, here's the visual. Here's the whole big M3 of R. which is like 9-dimensional. Now the matrices of trace 0, that's S, that's like 8/9 of M3 of R, because this is 8-dimensional. So all of the matrices that have a trace of 0 are right in there. It's 8-dimensional. So I've got to grab somebody out here. Right? I've got to grab a matrix that's not in S. And this one works just fine, right? Because the trace of this matrix is not 0. You could have picked, you could probably pick a random matrix. Chances are it will work, right? As long as it's outside of the span of the other vectors, this is going to still maintain linear independence. Right? So the first 8 vectors were already a basis for S, so they were already Li. You guys remember our theorem that if S is Li and V is not in the span of S, then S union V is still Li. This was theorem 1.7. That's what I did the first week I was here. Right? We proved that theorem. So this is a nice theorem. If you have a linearly independent set and you put another vector into your set that came from outside of the span of what you had before, you still have a linearly independent set. Okay, so this E33, so since, I'll just put a little justification here. Since E33 is not in S, right, then the set above, well, let me just say it this way. This set is still Li. This is by theorem 1.7. Guys, you don't need to know the theorem numbers. On the test, you can say by a theorem in class. Don't worry about remembering what number it is, okay? So, by theorem 1.7, this is still Li, and has 9 vectors in it, which is equal to the dimension of M3 of R. So remember, guys, if I give you the right number of vectors, 9 vectors in a 9-dimensional space, right? I have 9 vectors in a 9-dimensional space. As long as they are Li, well, then they will also be a basis. We had consequences of the dimension theorem, I think is where I mentioned that before. So, thus, by a result in class, you can say that, just make sure it was a result in class. By a result in class, right, beta is a basis. So that's actually what we wanted to have. Okay. All right. Does this kind of make sense, guys? All right. I am gonna change gears a little bit here. Yeah, Jennifer?
I have a question. So had it not been E through 3, what other vectors can you...
What else could I have put here? I could have put 1, 2, 3, 4, 5, 6, 7, 8, 9. Or anything that does not have a trace of 0. Anything. Actually, it's kind of cool to use E33. We also could have used E11. But here's the thing. By using, I like this. By using E33 together with the fact that I already had E11 minus E33, if I add these together, I get E11. And similarly here, if I add these two together, I get E22. Well, once I get E11 and I get E22, I'm going to win, right? Because I've got all the other standard basis vectors. I've got E13, E21, E22, E23, and so on. The other ones are all there. The only sort of diagonal, the only members of the standard basis for M3 of R that I don't have in the original 8 vectors are E11, E22, and E33. And if I throw in E33, then I can see how to make E11 and E22 as well, right? I also capture those vectors. Okay, but you don't have to. Like I said, you could probably just randomly throw darts at a board and put numbers into your matrix based on that, and you're going to get something that's going to work, right? It's just totally easy to come up with something for that. Yeah, so that's good.
But you just needed the trace of that to not equal 0. That
Right.
works? Okay.
Yeah, anything that has a trace that's not 0 is definitely going to work. Okay, let me give you another problem. Okay, let's try. Well, this will be interesting. Let's try this one. Okay. So here's another example. Is this number 4?
Yes.
Okay. Number 4. Let's take V to be P3 of F. So I'm taking polynomials of degree 3 or less. Don't forget about the or less part. These polynomials don't have to be third degree. If you take just the third degree polynomials alone, you won't have a vector space. It won't be a vector space. So you need to allow the polynomials to have degree 3 or less. Okay? And S is going to be the set of P of X, an element of V, such that P of 2 is equal to 0 and P prime of 5 is equal to 0. And part A of this question is going to ask, is S a subspace of V? Okay, and then if it is, then we'll follow up with a second part to the question. Is this a subspace? So I want you to be comfortable working with different types. So this problem was about matrices, right? Now this one is living in a polynomial context. So the objects are going to look a little different here. Okay. I'm sort of killing time while you guys, I'm just sort of chatting up a storm here while you guys think about whether you think it is yes or no, because this makes a big difference as to what we're going to do next, as to whether it's a yes or a no. What is the 0 vector, by the way, in this vector space?
0 plus 0x squared.
Right, exactly. So my 0 vector, just so we all are clear about this would be 0 plus 0x plus 0x squared plus 0x cubed, which is literally just 0. And if I was going to draw a graph of it, right, if I was going to draw a graph of this polynomial, I would literally just be plotting the x-axis, right? It would just be totally flat on the x-axis. So, for instance, if this had been P of 2 equals 1, this graph over here, so here's x equals 2, right? If I'm saying that P of 2 has to equal 1, well now my 0 function does not go through that point, and so we would be missing the 0 vector. So if this was the problem, it would be a fast no. It would take hopefully 30 seconds or less to just think about that and say, nope, there's no 0 vector there, so it's not a subspace. Okay, maybe a little more than 30 seconds, but it should be pretty quick. This 0 vector analysis is usually not something that takes that long to do. But let's go back and make that into a 0 again. So that means I'm moving this dot right to here. So we are looking at polynomials that go through that dot and that over here are flat. The derivative is 0. So, here's an example of what that might look like, some function like that. There's a function that's in S. What do you guys think? Do you think this is a subspace? Closure under addition and scalar multiplication is what I will have to do if I believe that it is. The other thing is, if you're not sure, you check the zero vector. I mean, the zero vector definitely satisfies these two properties. In fact, I should make a note here. Let's just note that the zero vector is in S, and we just put a check there. So I know that I've thought about that. If we really don't know beyond that, whether it's yes or no, you can try to start verifying closure under addition and see where it gets you. Okay, you can see if it's going to work. So I'm going to do that, and if it's not going to work, then somewhere along the line, hopefully we will catch ourselves where the problem is at. Okay, so I'm going to go ahead and put a closure under addition here. It's a little bit tentative right now because I'm not getting a lot of vibes that any of you are that sure about this one yet. So let's just take it tentatively, and we'll see how it works out. Okay. So I'm going to grab two vectors from S. Okay, well I can do that. Now, because these are polynomials, please don't call them capital A and capital B. That wouldn't really make sense in this type of a context. I would suggest that we use a P of X and a Q of X. I'm going to grab those guys. Those are elements of S. Okay, so that's my starting point. So then I'm going to come over here and I'm going to ask myself, what does this mean? If P and Q are in S, it means they satisfy this condition, right? They are cubic polynomials that satisfy this condition. So what we have is, we have P of 2 equals 0, P prime of 5 equals 0, Q of 2 equals 0, and Q prime of 5 equals 0. We have like all of those equations. Those things are all going to be true. So I'm just putting down the assumptions. So do you think that those same equations will be true about P plus Q? So closure under addition, we're going to be looking at the sum, P of X plus Q of X. Let's try and see if we can write it down. Let's see if it works. Okay. So let's look at P plus Q of 2. We're hoping it equals 0, but please don't write 0 here yet. I've got to work my way to that conclusion, if it's in fact going to work. What can I do with this? What's P plus Q of 2?
Maybe you could break it apart and say P of 2 plus Q of 2. I don't know how you justify that.
Oh, that's exactly correct, right? So if I have like, you know, sine of x, I know we're supposed to be dealing with polynomials here, but I mean if I have sine of x plus e to the x, and I want to evaluate that at x equals 2, right? Well, of course I can just plug the 2 into this part, and then plug the 2 into this part and add them separately. So that's exactly what we're saying right here. We're just going to figure out what is the first part when we plug into, what is the second part when we plug into, and kind of go from there. What is P of 2 plus Q of 2 going to equal? 0 plus 0, which is 0. Okay. I'm not ready to say anything about S yet because I have another condition here. I have to look at P plus Q prime of 5. So if I take the derivative of P plus Q and then plug in 5, how can I break that down? Jennifer? Right, P prime of 5 plus Q prime of 5. Works the same way. Derivatives respect addition, which is a beautiful thing. So you can differentiate separately, and that's just 0 plus 0, which is still 0. So those two things together, now we can say, therefore P of x plus Q of x is an element of S. So we took two polynomials in S, we added them together, and the result is still in S. Okay? So that's the first part. Okay, let's talk about the second part here. the scalar multiplication, right? We're going to look at that, see if that works as well. Are we feeling more confident though? I am. It's going to work. You know, if it doesn't work, it's boring. It's like, there's nothing we can do. If something's not a subspace, I can't really do anything, right? Okay, so let's see if we can get the closure under scalar multiplication. Can somebody give me the first sentence over here?
Let P of X.
Let P of X,
Yeah, belong to S. Oh, yeah.
actually, what's my rubber stamp every time I start this? I always start it the same way. Yeah, I'm just going to let this be as above, because I already wrote down what P of X was. And we just have to grab a scalar, which is C. Okay. It really is handy to just get used to starting the second part off that same way every time. Okay? So then, let's just look at C times P. And I need to evaluate it at 2. So we're just scalar multiplying our polynomial by C. We're then plugging in 2. But of course, I can do that by first just plugging in 2 and then factoring the C out of that. So we're just kind of regrouping it like that. But P of 2 is already equal to 0. So this is just C times 0, which is 0. All right? And we can do the same thing for CP prime of 5. Derivatives also respect scalars. The scalar can come out. We just have to evaluate the derivative of P at 5. And that's also C times 0, which is 0. And so C times P is an element of S. It is a subspace. So now, for the challenge problem, find a basis for S. This is the fun part. I couldn't ask you to do that until I knew that I had something that was a subspace. So I'm showing the subspace part first, and now we're going to find a basis for it. So I need some help from you guys on how am I going to do that? Obviously, the basis should have at most 4 things in it. We've learned that the dimension of Pn of f is just n plus 1. So this dimension is 4, and remember that one of the things we talked about in class is that a subspace has a dimension that's always less than or equal to the dimension of V. So we're looking for 3 or less vectors over here. The question is, how do we get them? Well, we're looking for at most 4, but S has enough restrictions on it that I actually know that S is not equal to V. So let me just make a note here. So since S is a proper subset of V, I can just write it like this, right? So this just means it's a subset, but it's not equal to V. Okay? The dimension of S is going to be less than the dimension of V. So we did have this result in section 1.6. Okay, so the dimension of V in this case is 4. So we're looking for something that is 3 basis vectors or less for this problem. Okay? Any thoughts on how I'm going to get it? Sorry, do you have an idea?
We'll start with the general form of vector in P3.
So just like we did over in the trace, in the 3x3 matrix example, we wrote down the general form of one of those matrices. We need to find the general form of this vector here as well. So to get this going, I'm going to take Robert's idea. I'm going to write P of X as a general cubic equation here. So ax cubed plus bx squared plus cx plus d. Okay, that's a general form of a cubic or lower degree polynomial. Okay? What can I do with that? Bruce?
We can have it for P of 2.
Okay, we know that P of 2 has to equal 0. So we can put 2 in for x here, and it's going to create an equation for us, right? So now we know that 0 is equal to P of 2, right? And so if I put the 2 in for the x, I'm going to get 8a plus 4b plus c, and then plus d. Okay, so that's equal to 0. Let me just put the 0 on this side as well. This is actually a nice equation that will help us to solve
Oh yeah, 2 instead of 3.
2c, yep, that should be a 2c, thank you. 2c plus d, does that look better? Right, so this is one of our equations that we can work with. Occasionally I'd like to just make an occasional mistake on purpose here and there, just to see if everybody's awake and paying attention. So there was a missing 2 there, Robert caught that. So okay, let's go on and figure out what else we can say. Bruce, you're...
Oh, sorry.
Sorry, I was going to say, Bruce, you're on a roll. What else?
And do you do the same thing for the derivative?
Okay.
P prime of
We've got p prime of 5 right here, right? So I should be able to get an equation out of that as well. In order to do that, I actually will need to take the derivative of my p of x. So I'm going to try not to erase the set S here, because this is kind of the whole problem is based on this set right here. But let me go ahead and try to get some space, and we're going to... So you see, we actually have to get our hands messy a little bit on this part. We have to actually write out the form of these polynomials. Okay, so let's take the derivative of p prime of x. That's going to be 3ax squared plus 2bx plus c, right? And we know that if we put in 5 into that, we're supposed to get 0. So p prime of 5, well, if I put in a 5 for x, I'm going to get 75a plus 10b plus c, and that is supposed to be equal to 0. So I have created 2 equations here that involve those coefficients a, b, c, and d. Okay? What would you like me to do now that I've created those equations? I can set them equal to each other, but they're both equal to 0, right? This one's equal to 0, and this one's equal to 0. If I set them equal to each other, that's actually kind of less information than keeping both equations in my sights. But what could I do?
Put it in the matrix.
Put it into a matrix. That's exactly right. We just want to create a system. We're just going to create a system here. So I'm going to make a matrix. The first row is going to be an 8, and then a 4, and then a 2, and then a 1, augmented with 0. And then the second one is going to be a 75, and a 10, and a 1, augmented with 0. Okay, these numbers are not looking that nice. Okay, I have a confession to make. I made up this problem in my head right at the start, so I can't promise that these numbers are going to be that nice. But let's just see. I really will for the exam. Like on the review session, I don't worry as much, but on the test, I'll try to make sure that the numbers are not bad. I don't know if I ever actually said this, but we're not going to use a calculator on the midterm. It's just going to be pencil and paper, because I'm not interested in getting a messy ERO problem. But the trick to doing these is always to get a 1 into the upper left corner. So as much as I hate to bring fractions into it right away, that's kind of what I need to do here. I'm going to divide the first row through by 8. And then I'm going to leave the second row the same for a moment. My little twiddle just means I'm doing an ERO. It's hard to imagine a linear algebra class review for 2 hours without doing an ERO somewhere. So here it is. The first row is looking pretty good. Pretty good so far. So